Okay, all right. So let us begin today's session. First of all, a very good evening to all. And in this today's session, we are going to see the power loss of typical radial distribution feeder. And in the last session, we have seen the problems based on the typical structure of pyramid distribution system, in which we have seen many Vaswara schemes for the pyramid distribution system, and we have solved many theoretical problems based on the power distribution networks, a brief overview. So now in this live tutorial session number 4, we are going to see mainly the problems based on the voltage drop for typical radial distribution feeders. And before we start solving the problems, let us first go through the uh, go through a summary of what we need to know before solving the problems. We will see some expression, we will see some terminology before we start to solve the problems. So let us have a quick recap. So the first term comes here is the K constant. So K is a constant that can be defined as a percentage voltage drop per kilovolt ampere mile. And the expression for K constant is written that R cos theta plus X sin theta into 1 upon third into 1000 upon VR into V base, and its unit is voltage drop per unit per kVA mile. So this unit is very important. If it is not multiplied with 100, then it is voltage drop per unit per kVA mile. If it is multiplied by 100, then percentage voltage drop per kVA mile. And the here in K constant, this R denotes the resistance per unit length, X denotes reactance per unit length, cos theta power factor, V are receiving in per phase voltage, and V base is the base phase voltage. So now let us see what is the significance of K constant. So I have taken this figure 4.26 from the Turan Gonen book, Electrical Power Distribution System Engineering. So this figure provides the K constant for various voltages and copper conductor sizes. So here, if you see in this x-axis, we are having this copper conductor sizes that is given in AWG or MCM. And in this right hand side, y-axis, we are given the line-to-line voltage. Like this K constant is given for 2400 volt, 4160 volt, 4800 volt, and so on. And in this left hand side, we are given with K constant. And this K constant is percentage voltage drop per kVA mile. So if you refer this figure, then we can see that I think someone mic is turned on. Please turn off your mic. So this figure is developed for these 3-phase overhead lines with an equivalent of 37 inch between the conductors. So this is already specified, and this if you see this how it varies with copper conductor and line to line voltage, then you can see that as the line volt increases in the right hand side, if you see right hand side y axis, this line volt increases, K constant decreases for each conductor sizes. So this is matching with our expression also. And if this x axis, as the cross section area of conductor increases, the K constant decreases for each voltage levels. So it is obvious that if the cross section area of conductor increases, then its resistance will reduce, and this power loss will reduce, and then voltage drop will also reduce. So in that way, we can say that this K constant also reducing for increasing this cross section area, and also this K constant decreases upon increasing this line voltage. So from this figure you can clearly understand that what is the significance of K constant. This K constant decreases upon increasing the voltage level and upon increasing the cross section area of conductor. So this K constant is basically this voltage drop per unit per kVA mile. So this is basically a unit. So K constant is the percentage voltage drop per kilovolt ampere mile.
Sir, this hello, hello. Hello.
Actually, I mean, uh, my college, this whenever power cuts, then internet connection goes out. That is the problem.
Yes, sir. Okay.
I hope you are.
Yes, sir. I have one doubt.
Yes, yes.
That means our constant K depends upon, as per you discussed, it depends upon material used and the space between line and types of loads.
I think this question is asked from the in this current assignment,
Yeah, yeah.
right?
That means it not depends upon load density.
No, no, I cannot. I could not give the answer directly, but
Yeah,
you
yeah.
just
No
see.
need to give directly. I just discuss based on your slide only.
Yeah, so from the slide you refer, you can refer my slide. Otherwise, you can refer class notes.
Okay,
This
okay,
material of input.
okay. Thank you.
Yeah. So now let us come to this power loss and voltage drop computation for the radial feeder with uniform distributed load. So here we are having this distribution LV bus substation, and then this circuit breaker, and the central line is primary feeder. And from this primary feeder, these laterals are connected, and these nodes are denoting load points. So for this structure, of radial feeder, primary radial feeder with uniform distributed load, we can find the voltage drop and this voltage drop will come out of ISZL. So here you can see this, if nothing, it means voltage drop of a radial feeder is directly written as ISZL, where Z is impedance per unit length. And like this is informally distributed load. So if you take the L equivalent or L effective, this comes out as L upon 2. So that's why this, if you compare this voltage drop with is similar to a lump load connect at the midpoint of feeder. So this L effective is comes out as L by 2. So by comparing with this lump load connection, you can find the L effective or equivalent effective length or equivalent length of the primary feeder. Now for this informal distributed load, if you find this total power loss, then it comes out at one third of IS square RL, and this loss is given it per phase power loss. If they are asking three phase power loss or total power loss, then you have to multiply with a third. Then now again, if you compare this with this lump load connected lump load for this ready primary feeder, then this L effective is coming as L upon 3. So L effective or L effect equivalent we compare with the connection of lump load. Now in this previous one, we have informally distributed load, and now similarly we can find the voltage drop and total power loss for informally distributed load with triangular service area. So earlier this is rectangular service area. So this one is rectangular service area. And in this one, we are having triangular service area. So for triangular service area, this voltage drop expression comes out as 2/3 of ISZL. So here in this top corner, I have written for the lump load connection, and we are finding the L equivalent with this connection only. Means this is LV bus distribution, LV distribution substation, LV bus, and then circuit breaker, and this is primary feeder that is providing power to this lump load. So for this case, if you find voltage drop, then it will it will come out as ISZL, and total power loss will come out as IS square RL. Now for this triangular service area, we have found out this voltage drop as 2/3 of ISZL. Therefore, we can tell that this L effective or L equivalent is 2L upon 3. And for total power loss, it will come out as 8 upon 15 I square RL. Therefore, this L effective or L equivalent will come as this 8L upon 15. It You can assume this at a distance of 8L upon 15. This lump load is connected to this primary feeder. So X is nothing. So this is
assumption, sir.
S.
This distance is assumption of our derivation.
No, this is not assumption. We are comparing with this expression where we have concentrated lump load for this primary feeder. Effective length of primary feeder. And similarly, for power loss, effective length of primary feeder will be 8L upon 5. So this one is total length of feeder. L is total length of feeder, and L effective is effective length of feeder, primary feeder. I hope this is understood. And for derivation, you can refer the our course slides. I have just providing a summary. In this previous slide, we have seen this primary feeder with uniformly distributed load, where we have the drop and total power loss expression is given. And for the triangular service area, we have this voltage drop and total power loss. Any anyone having doubt till here?
Yeah, sir. That means in triangular area, we are considering 2L by 3
Yes,
effective for a voltage drop, and our square area we are considering 1 by 2.
yes, correct.
Yeah,
Very good.
in this
That is
slide,
the summary.
yeah, one VD equal to 1 by 2 in the, okay, in this this slide, what you wrote in the right hand side, top side, VD equal to IS by ZL.
So
Top
this,
side,
yeah, from here we are comparing the things. Like here we have this is lump load.
this is not square or triangular. This is basic formula.
This is lump load. Then how we will find the voltage drop for this feeder. The voltage drop is I into Z. So IS ZL. So Z is per impedance per neutral length, and power loss is I square R. So R is resistance per neutral, so may be multiplied with L.
Yeah, this is for square or a triangular area.
Again, you misunderstood. Means like in the right hand side, how you are telling this effective length is 12 by 3. Like this is our primary feeder having uniformly distributed load with triangular service area. Now you just removed all the load, and how will represent the load such that this voltage drop will come similar and total power loss will come similar. Like you just remove these loads. These are nodes, and where these load connections are there. So you just removed all the nodes. Now you have to make the you have to make the connect you have to provide the power to the load at which point shows that voltage drop will be similar to this lump load connection. So you will having this lump load at single point. Like suppose here you have provided this all loads this that are uniformly distributed. Now we have just single load, that is lump load, and single load at a distance of 2L upon 3. Here only all the loads are connected. This you can say as lump load, and you have removed all the loads. So this is radial feeder, and this is lump load, means all uh, equivalent load of this all the loads connected to this primary feeder rectangular service area. You got my point or not? Now
Yes,
this
yes.
lump load is having distance 12/3. So for this case, if you find voltage drop, then this voltage drop is I into Z. So IS is the current that is coming from out from the substation. So IS, and this Z is per unit length impedance, and effective length is 12/3. So the similar expression will come that for load service area. This for the comparison basis, from this comparison only we are finding this effectively. We are comparing with this lump load connection, not with uniformly distributed load.
Okay, thank you, sir.
Okay. Now moving to this distribution substation service area. So this distribution substation service area can be of different shapes, and there is mainly focused two structures, that is a square based substation service area and hexagonal substation service area. So there are some assumptions we have to keep in mind. This we have considered that substation is located at the center of service area, and second assumption is that load distribution is uniform over the entire service area of substation. So let us see this a square based substation service area and hexagonal based substation service area. So this is square based substation service area. So in this square based, you can see this center one. This is a primary feeder, main feeder, and these are these nodes where this feed loader. These are laterals, and in the laterals we are having load points that we call as nodes. And this since this number of feeders are four, like you can make this side, you can make this side, you can make this side. So total number of feeder 4. So that's why we have denoted L4. So whenever we are writing L4, this 4 is denoting the number of feeders. And a square substation service area means we have 4 number of primary feeders. Similarly, in this hexagonal substation service area, this one is a square substation service area. And this is hexagonal shape substation service area. So in this hexagonal means we have 6 number of primary feeders, and L6 6 denotes that number of primary feeders. So 6 number of primary feeders. And here L4 denotes that length of primary feeder. So if you understand all the term here we are using, then you can clearly understand the expression and you can solve the problem easy. And in this L6, L6 denotes the length of primary feeder in hexagonal shaped substation service area. So now we have one term also we denote as area served by one of the feeders. Means like there are 4 feeders and this you denote as A1. This denote as feeder 1. Feeder 1 means uh, primary feeder number 1. So this area comes under this primary feeder number 1. So the area served by this figure we called it as A1. A4 because here 4 number of primary feeders. So and similarly for this area served by this one of the feeder in hexagonal shaped service area we denote as A6. So A4 means area served by one of the feeders. And A6 means area served by one of the 6 feeders. So this area served by one of the 6 feeders. So we are using this server script 4 or 6 by the number of primary feeders. So don't confuse with these other things. This A4 means area served by one of the 4 feeders in this for the square shape, and A6 means area served by one of the 6 feeders that we denote for hexagonal shape. Now before we move to this square shape and hexagonal shape, first see this substation service area with single and double primary feeders. That is the uh, very basic one, and the question in that assignment we don't ask question based on this single and double primary feeders. So if you see this single primary feeders, then we have substation, and this is the primary feeder. And if you consider uniformly distributed load that is having a square based service area, rectangular based service area, like these are nodes, and sorry, these are laterals, and it is having nodes. So uniformly distributed uh, loads. So for this case, we have seen this L effective. So L effective, we know this L1 upon 2. So this is length is total length of the feeder is L1, and for this area served by this primary feeder will come out as A1, and this is L1 square. So voltage drop will come as K into L effective into area in this power coming out from this primary feeder, and S1 we denote as based on this power density. So S1 is D into L1 square. You can also write D into A1, and A1 is D L1 square. So this will come as K into L effective is L1 upon 2, and S1 is DL1 square. Now for N, if we are having double primary feeders, so these two are primary feeders. Let us assume this length of primary feeder is L2. Similarly, we are this uniformly distributed load with the laterals. So for this case, area served by each primary feeder is L2 square, and then S2 will come as D into A2, so D into L2 square, and L effective for uniformly distributed load with rectangular service area is L2 upon 2. So voltage drop is K into L effective into S2. So K into L2 upon 2, S2 is D into L2 square. So this is the basic one, but in the assignment we don't have problems based on this single and double primary feeders. But for understanding, you can correlate with them. Now for this substance service area, we will see the general case, and then we will put all the expression for a square shaped substation service area and hexagonal based substation service area. So this general case is applicable for this n greater than equal to 3 only. This is because if you see the expression of area served by one of the feeders is n equal to ln square tan theta, and this theta be represented 360 degree upon 2n. Now here n represents the number of primary feeders, and if you put n equal to 1, then this come out as tan 80 0. So this area will be equal to 0. So this is invalid for n equal to 1. And also if you put n equal to 2, then theta will come as 90 degree, and tan 90 degree is infinity. So again area served by one of feeders will be come as infinity. So that's why this general case, whatever we are seeing here, all the expression is applicable for equal to or greater than 3. So that's why we have seen the separately with single and double primary feeders. And now we will see the case with when substation service area with having number of primary feeders is greater than or equal to 3. Now the KVA load served by one of the feeders we denote as SN, and N denotes here number of primary feeders. SN equal to D into AN, and AN denotes the area served by one of the feeders, and D is load density. Load density is kVA per mile square or kVA kilometer square based on the unit of length for the primary feeder. And now the other expression is percentage voltage drop of the main feeder will be K into LE into SN, where L is the effective length. So here I have written this total lump load is concentrated at a point on the main feeder at a distance of 2/3 of ln from the feed point. So that represents the effective length, and effective length is coming as 2/3 of ln. So we have seen for triangular service area where we are the effective length is coming out as 2/3 of ln. So now in this percentage voltage of KL into Sn, if you substitute all this value like Sn, first substitute Sn equal to D into An, and then put An equal to ln square tan theta. So go reverse, go in reverse direction. So this is the percentage voltage drop expression. Now we substitute first D into An expression here, and then substitute An equal to ln square tan theta. Then you will get this term A into 2/3 D ln Q tan 360 degree upon 2n. So this is the I have shown here also. This first one is K L E into Sn. Now we have substituted effective length as 2/3 of ln, and in the next step we have substituted the service area served by one of the feeders equal to D into An, and again we substitute this area served by one of the n feeders ln square tan theta, and we know that tan theta equal to tan 360 degree upon 2n. So substitute all this value, you will get the final voltage drop expression. Now let us see this if you having n equal to 4. N equal to 4 means a square substation service area. So this is for a square substation service area when n equal to 4. So n equal to 4 means a square substation service area, square shaped substation service area. So if you having n equal to 4, then theta comes out as 45 degree and tan theta equal to 1. So percentage voltage drop is K into 2/3 D into L4Q. Now if you are n equal to 6, means number of primary feeders is 6, then theta will come out as 30 degree and tan theta will come out as 1 upon root 3. So this percentage voltage drop will come out in this expression, and this is for hexagonal substation service area. In similar way, you can also found for if you are having this number of primary feeders is 8, that is octagonal substation service area, you having theta equal to 22.5 degree and tan theta equal to 0.412, and in that way you can find this percentage voltage drop. We are mainly focused on a square substation service area and hexagonal substation service area. So we have covered all the means basic things for this current assignment that we need to know, and in the last we will just have one table that some problems are also based on this table where we have to interpret this voltage drop formula, means how this voltage drop will be affected upon changing the length of feeder, on changing the K constant, on changing the number of feeders, or changing the load density. So if you change the length of feeder twice, then percentage voltage drop will be 8 times. And if your load density is twice, then percentage voltage drop is proportional to load density. So it is also been twice. And adding new feeders is twice, then this area served by one of feeder will reduce by half. This percentage of voltage drop will also reduce by half. Till here, any doubt? Then if anyone having doubt, then you can ask. Otherwise, we will move to the assignment problems.
We can move, sir.
Okay. So the first problem is that you are having a three-phase star connected grounded feeder main with a receiving voltage of 4.16 kV. The feeder main is made of copper conductors and arranged with an equivalent spacing of 37 inches between phase conductors and operating at lagging load factor of 0.9. The conductor spacing given as this resistance and reactance per mile. Assume the base voltage as 2.4 kV. You have to find the constant gain percentage voltage drop per kVA mile. So here I am writing the expression. You also try yourself. If anyone got the answer, please type it in chat box. You can speak also. Okay, constant. We know that per unit voltage drop per kVA mile is r cos theta plus x sin theta upon VR V base 1/3 thousand. So you also write it units. Unit will help you in solving these problems very easily. So its unit is voltage drop per unit per kVA mile. Now you have to just substitute all this value. So what are things we have given? So this is the expression. So things given here as R equal to 1.503 ohm per mile and X is given as 0.7456 ohm per mile. So now cos theta is given as lagging load power factor of 0.9. So cos theta is 0.9 and then sin theta is 1 minus root 1 minus cos square theta 1 minus 0.81 under root. So it will come out as 0.4359. Now VR V base is both are same, rated voltage and base voltage both be considered same. So base voltage is given as 2.4 kV, 2400 volt. So all things are given. You have to just substitute all this value. You will get the answer. A equal to 1.503 into cos theta is 0.9 plus x is 0.7456. So sin theta is 0.4359 into 1/3 of 1000. upon VR VBS. So also write it in voltage drop per unit per kVmi. So VBS is 2400 volt square. So it will come out as 559.233 upon 2400 square. So 9.7089 into 10 to the power minus 5. So you can write 0.00097 voltage drop per unit per kVmi. So this is, we got K constant in terms of per unit. So we have to write in percentage.
VR and VVS both are the same value.
Yes, both are same. If they have not written different in the problem, they have not separated like rated and base voltage different, then you consider both as same. Generally, one thing given, and then you have to consider both as same.
Noted.
So multiplied with 100, so we get the answer in percentage form. Percentage voltage drop per kVmi. Correct answer is A. Today attendance is more than previous class.
Sir, I have one doubt. Actually, now
Yes.
we are calculating the constant K.
Yeah.
Yeah. In this, as per this formula, there is no this constant have no any dependency of current.
Yeah. No, it is not depending on this current.
Yeah, it depends upon our resistance, inductance, and for example,
Voltage.
power factor and voltage.
Yeah. Correct.
That means R and X depends upon the material of the conductor, and power factor also depends upon the type of load and
Yeah.
voltage only.
Yes.
There is no any relation with the magnitude of current.
Yeah. Yes.
Yeah. Okay. Thank you.
So for the current assignment, I think question 9 is what you are asking is similar. But I would just say like I am also not able to provide this. I will
Yeah.
not able
Yeah.
to provide you hint.
Yeah. I just asked
So
based on
don't
that one only. I am not asking directly, sir.
Yeah, that, but I'm also not knowing the answer. That is true.
Yeah, it's okay. Thank you.
So it's like don't believe, means you don't further claim that I told you to
No,
put
no,
this
no.
answer. Because it may be wrong. I should not confirm.
Okay.
Because we are only assigned to solve the previous assignment.
Okay.
Because this course is purely advanced course, not basic one. So there may be some interpretation, further study. Means many things are, many literature you will find many things, and you have to go on one conclusion. So it's like you are saying this thing, some other person will also come and say this. Maybe you can see in this way, other way. Research based course or advanced course, they have some like contradiction always. So
Yes, yes.
so I know this formula only, and I just show two slides that I know, and in this I'm in problem 9 I'm also little bit honestly saying I'm also little bit confused. So it may be wrong if you put on my, means like whatever I said in the class. So, but whatever I am solving problem here, it is true.
Okay, noted, sir.
And theoretical problems are always like more tougher than numerical problems. Right? Theoretical problems, there are many assumptions and many things will come in between, and many will give their own opinion. So theoretical problems are always tougher, means always having more chances of mistake. So I don't like theoretical problems actually.
Okay.
So let us move to the next problem. So in this problem, assume a lump sum load of 250 kVA with a lagging load factor of 0.9 is connected at the end of 1 mile long feeder main. Calculate the percentage voltage drop in the main. And option is 1%, 2.425%, 1.12%, and 1.617%. So this one is very simple. So if you know this percentage voltage drop, as we have seen, how we can write percentage voltage drop? K into this K is voltage drop per unit, voltage drop, percentage voltage drop per kVA mile. So K should be multiplied by L, so that length will cancel out. So K into LE into ASN, or you can write S3 phase. Since this is for, so write S3 phase. So this is expression for percentage voltage drop. Now in the previous question, we have found this K value. So K we got from first number problem, 0.0097 percentage voltage drop per kVA mile. We got from the question 1. Now you have to substitute this value here, and effective length is, so this is lump load. Here they are saying that lump sum load. So effective length is L only, and this L is coming given as 1 mile. So L is given as L is given as 1 mile. And S3 phase is given as 250 kVA. Percentage voltage drop will be then 0.0097. So always write all the units. So there is less chance of mistake. So 0.0097 percentage voltage drop per kVA mile. Now L is given as 1 mile and S3 phase is given as 250 kVA. So all things will cancel out. Only percentage voltage drop will be here. So this percentage voltage drop is come out as 2.425%. So correct answer is B. You also try yourself and you parallelly solve with me. You can also try to answer chat box. I'm not getting response today. Now let us move to the next problem. In this problem, all the things are same. They are asking that yeah, in the last problem is lumped load, but here it is saying that uniformly distributed along the feeder main. So here, if you see in this problem, this L effective is same to L because due to lump load. But now in this problem third, they're saying that the load is uniformly distributed along the feeder main. Right. So what is the effective? Can anyone tell?
Can you share question third?
Question 3. L effective will be L or L by 2. Here in this uniformly distributed load.
L by 2.
Yes, this is L by 2 because load is uniformly distributed. And previous question, this lump load. So that's why we have to not see any other thing. L effective is equal to L only. So now that is difference only. So L effective will be L by 2. So what will be percentage voltage drop? Can anyone tell? In the question 2, we got percentage voltage drop as 2.425%. 2.425%. What will percentage voltage drop here? It will be same or it will be half or it will be double.
Half.
What?
It will be half.
Yes, correct. Very good. So it will be half. L effective will be L by 2.
That means if we mention in the question uniformly distributed, we have to take the L by 2.
Correct. But for this, since this is a single feeder, that's why you have to tell L by 2. Suppose you are having this a square, what that is said, a square shaped substance service area or hexagonal shaped substance service area that is having each feeder is providing triangular substance service area. Then L effective will be 2L upon 3. So here they have not considered this substance service area that is a square shaped or hexagonal shaped or any other octagonal more than a number of feeders is more than 3. So in this they are saying that in this figure they are only single feeder. That's why L effective will be by 2. If triangular shaped substance service area, then L effective will be 2L upon 3. Right? One 1.2125. The correct answer. So C is the correct answer.
The answer is directly giving a percentage. No need to multiply 100. Huh?
Because this K is given in percentage. We have in first question, we have calculated K in percentage. So that's why answer is given in percentage.
Oh, okay, calculated in percentage. Okay, okay.
Yes, yeah. That's why I told you write in its unit. If K is given in voltage drop per unit, sometimes they wrote in voltage drop per unit. So then the voltage and this drop will come in per unit. So you have to multiply K so that you will get percentage voltage drop.
Okay.
So I am curious to know your name because your name is coming as other thing, your mobile.
Yeah, yeah,
Right?
I'm joined from my name is Shihab Abdul Wahid.
Okay.
I am from NIT
You're from
Calicut. NIT Calicut.
okay, nice. So you are a student or
Again,
your
sir?
master student or PhD
No,
PhD student or master
I
student?
am PhD student in power system.
Great. When IIT Calicut this time NPC is going to happen. You know this thing?
Yeah, yeah, I know.
And we are writing paper for that conference.
Yeah, conference. Okay, okay. Thanks.
Because last time this NPC happened in our college IIT Guwahati.
Oh, got it. Okay, okay.
And my guide Chandan Kumar was the main
Main
chair,
coordinator. Okay, okay.
um, chair for that conference.
Okay.
So let me first, I will just give you this problem and I will switch to my college Wi-Fi. I think 1 minute maybe again interrupt. So you just uh, write this question and it will come in 30 seconds. There may be some again internet problem. I'm switching over to college Wi-Fi. So here in this problem, you have to determine the substation size. And all the means you write the data and you try to find the substation size. Are you able to see the screen? Hello? Hello?
Yes, sir, we can see.
Okay, then. So you start from this question number 4. You have to determine the substation side. And in this, if I give you hint, then this in this problem, the feeder is thermally limited to 250 ampere. This feeder is thermally limited to 250 ampere. Thermally limited feed means its ampacity limit is given as 250 ampere. So I4 is given as 250 ampere. Why we have written I4? Because this substation is having a square shaped substation service area and that's in 4 identical primary feeders. That's why we write subscript 4 everywhere, I4, F4, S4. So you also try yourself. You can type on chat box. So maximum load per feeder is maximum load maximum load per feeder is S4 equal to root 3 into line to line voltage I4. So root 3 into line to line voltage given as 11 kV and I4 is given as 250 ampere. Thermal limit or its ampacity limit is 250 ampere. So S4 is coming as 4763.14 kVA. So this is the kVA served by the one of the feeders. Now they are asking about the substation size. So what should be substation size? Anyone can respond? So this one is we have found S4. So they are asking about substation size. So S4 means what? S4 is S4 is kVA load served by one of the feeders. served by one of the primary feeder. Now they are asking about the substation size. Can anyone tell? I am giving here hint that in this substation we are having 4 number of primary feeders. So what should be substation size?
Uh, Answer is J.
No, answer is which one?
Same
B
4763 A.
B.
No, B is correct. Answer is not same. This is KVA load sub one primary. They are asking for substation size. Who said B?
B.
Okay, DV. Yes, you are correct because as I said means like this we are having substation service area. This is this substation. So if you make this one primary feeder, then this is primary feeder, this is primary feeder. There are 4 number of primary feeders. And each primary feeder is having triangular shaped service area, right? So this one is feeder 1, and suppose this is feeder 2, and this is feeder 3, and this is feeder 4. So area served by one of the feeders is we called it as A1, A4. Sorry, because since 4 number of feeders, we call it as A4. And this is area served by one of the feeders, and then KVA load served by one of the feeders is S4. So since 4 feeders are there, then total substation size all are coming from this substation. So we can write since there are 4 number of primary feeders, therefore the substation size is 4 times of S4. So substation size is TS4, so 4 times of S4. So we have multiplied with all 4 because we have to take all 4 subsize. We have to take all into considered. So 4 into 4763.14. So it will come as 90,052.56 kVA. So B is the correct answer. So in the problem they are given everything. So a square service area. So that means 4 number of primary feeders and substation is located at the center of service area, and the service area which is triangular with uniform load density of 1000 kVA per kilometer square. Now coming to the next problem. In this problem, you have to find the length of each feeder. So here I will provide you one hint. So we have seen the expression of KVA load served by one of the feeder. So we have seen expression for KVA load served by one of the feeder is S4 equal to D into A4. So take the help of this expression, you will get the answer. So I will also write this S4 we got from the previous problem. So S4 we got as 4763.14 kVA. Now you have to find this A4. A4, we'll know that A4 is, so if you write the general expression, first I will write this one, tan 45 degree. So this is A4 expression. And if you remember the general expression of this AN, then this is coming as AN equal to ln square tan 360 degree upon 2n. So if you substitute n equal to 4, then you will get this expression. Now everything is known. You have to just find the L4. So length of each feeder means you have to determine the L4. What is the load density they have provided? They have provided load density as, so informed load density they have given. So informed load density means 1000 kVA per kilometer square. So anyone got the answer? So type your answer in chat box. Those who are getting the answer. Because in this assignment you have to do the calculation, otherwise you will not get the correct answer. And also I would advise don't take the help of AI, means chat GPT, other AI platform. They many times they are giving the incorrect answer. Yes, correct. 2.182. Correct. Deep, you are correct. So S4 is given as 4763.14 kVA. D is given as 1000 kVA per kilometer square, and A4 is given as L4 square. So all are in kilometer. So this L4 will come as under root of 4.763 kilometer square. So it is 2.1824 kilometer. So A is the correct answer. Now let us move to the sixth problem. So in this problem, they are asking the percentage voltage drop from the feed point to in point of the main. So I am writing the expression of percentage voltage drop, and you kindly solve this problem. KLE into SN. And let me also write all the values. What are things given here? So given things are K is given as, so percentage voltage drop of the feeder is given as this one. So this is nothing but K constant. So K is given as 0.0005, and this unit is given as percentage voltage drop per kVA kilometer. And then this informed load density is given as 1000 kVA per kilometer square. So D is given as 1000 kVA per kilometer square. Now LE is given as, since this is a triangular service area and a square shaped triangular a square shaped substation service area, so L effective will be 2/3 of Ln. So 2/3 of L4, and L4 we found from the previous problem, and L4 is given as 2.1824 kilometer. So from there you can find the L4. And the next thing we have S4. S4 is D into A4. And for this square shaped service substation area, A4 is L4 square tan theta. And we know that for a square shape, tan theta equal to 45 degree. So it is DL for a square. So I have provided all the things here. We substitute all this value, we will get the percentage voltage drop. So I am coming in 1 minute. I think I got some response. Try this problem. Ramesh is saying C. No, your answer is correct. Incorrect, Ramesh. Answer is B. Div, you are correct. Very good. B is correct answer. 3.4665%. You just have to substitute all these values. So percentage voltage drop K is given as 0.005 percentage voltage drop per kVA kilometer, and effective length is 2/3 of L4. L4 we have found 2.1824 kilometer, and then this S4 is coming as D into L4 square. So D is given as 1000 kVA per kilometer square, and L4 square is given as 2.1824 square kilometer square. So you will get the answer as 0.005 percentage, sorry, into 2/3. So if you take the cube of this one, 2.1824, then you will get 10.395 into 1000. So it will be 3.465%. So correct answer is B. Yes, B is correct answer. Now let us come to the 7th number problem. So it is very simple. No need to do calculation. So in this, they are asking about that if the number of feeders for the problem given in question 6 is doubled, keeping all the other parameters constant, such as length of feeder, load density, total service area, and base voltage, determine the percentage voltage drop. So I am giving you here hint. So take the help of this table. Let me put this figure. So here, what are things given? You have to find the percentage voltage drop. So from the question 6, from question 6, percentage voltage drop is given as 3.465%. Now in this, they are saying that number of feeders is doubled. Number of feeders for this problem is doubled, and other parameters are constant. So find the percentage voltage drop if the number of feeders is doubled. I am just giving you hint from, you can take the help of this table.
D.
B half D.
Is correct. D is the correct answer. Ramesh, and you are also correct. So if the length of feeder gets doubled, if the length of feeder gets doubled, then if you see the expression, final expression, then it is k into 2/3 of L4Q into D. So if number of feeder is double, then load under a feeder reduced by half, which results in voltage drop to reduce by half. But here, if you see where it is, yes, this one. Yes, sorry. So this, if you see this number of feeders is double, then area served by one of the feeder is half. Then this percentage voltage drop is also reduced to half because gets load under a feeder to be reduced by half.
Sir, in exam also the same pattern. One question is continuation to other questions.
Yes, there are high chance
Okay.
with the number because they will follow this assignment pattern.
Oh, okay.
Number of feeders is double. Creates load under a feeder. To be reduced by half. So, the load under a feeder to reduce by half, then which results in voltage drop to also become half. Which results in voltage drop become half. Now moving to the next problem. I think the similar type problem is asked in this current assignment also. I hope you all you all have tried. So in this problem, they are asking that longest primary circuit consisting of 2 miles main. So this is the primary feeder is 2 miles long and the most remote laterals A and B are given here. The value of constant K for lateral and the main feeder are given as 0.002% and 0.0015% voltage drop per kVA mile respectively. The load on lateral is uniformly distributed and the load on main feeder is lumped at the end. Determine the percentage voltage drop at the end of main feeder. So they are asking about the percentage voltage drop at the end of main feeder means at this point. And they are also saying that this main feeder is lumped at the end. So effective length equal to total length. So first write the important points here. The important point is given for the main feeder is that load on is very simple problem. You just solve in half minute. Is lumped at the end. So since the load on main feeder is lumped at the end, so this one that is 2 miles long. We know that let us take again internet interruption. To see the screen. Hello, the screen visible.
Yes, yes.
Okay, good. So here this let us consider this voltage drop one for the main feeder. Now we find the percentage voltage drop at the end of feeder. So try yourself. It's very simple. So for the main feeder, what is the value of constant K? K is given as 0.0015% voltage drop per kVA mile. K is given as 0.0015 percentage voltage drop per kVA mile. And LE is how much? Can anyone tell? Effective length.
2.
LE is how much? Yes,
2.
2 miles. Correct. And now SN is how much? If there is one feeder, then you better use S3 phase.
1000.
Yeah, correct. Very good. So SN is 1000 kVA.
The answer is A.
You just is correct. Answer is A. The percentage voltage drop is 0.0015%. L is 2, SN is 1000.
Are
So
you
it
writing
will come
something?
in.
You're not seeing any writing.
Yeah, I am writing. It is not coming.
No, only the one line is green. That's all. The first line. Load on main feeder. After that, nothing come.
Maybe network issue from your side.
Power due to power cut, I am facing this problem. Let me share the screen one more time. Now I think visible.
No, sir, not
Correct.
not visible. Either you can switch up your camera for more connectivity, better connectivity.
No, nothing.
Okay. I switched off the camera. Now it is visible.
No, but you are using two camera, one for the board, one for your video, is it?
No, I am using only one camera. This camera should be on as this NPTL session. That's why I always keep my camera on.
The screen is sharing the same connection or different connection?
Let me try one. How it is coming or not?
No.
No, sir, it is not coming.
Okay, then I again move to this college Wi-Fi, but this is college Wi-Fi is due to power cut always disconnected and take 2 or 3 minutes time. I think now it's clear, right? Hello?
Yes, sir. Now it is showing. Yeah, it's okay.
Yes,
It's
sir,
okay now.
clear. Now okay.
So this one is quite simple. I hope you understand. So let us move to the next problem. So the next problem, you have to find the percentage voltage of primary circuit at the end of each lateral. So they are asking about at the end point, what is the percentage voltage drop? So you can say at this point, either A or either B. So here they are asking about the percentage voltage drop of the primary circuit at the end of each lateral. Total percentage drop. So we have found this percentage voltage drop one, that is coming as 3%. Now let us consider for laterals as percentage voltage drop 2.
We
So
can
percentage,
write it without calculation. B.
yeah, correct. B is correct. Very good.
Because all others are less than 3, so we can directly write.
Yeah, very good. Yes. From the option you can clearly get the answer. Right. Very good. Nice. So you have to very attentive and use your mind in option. Very sometimes they provide very easy problem. So now if you solve a step by step, then percentage voltage drop for lateral feeder first find. Since they are given the load on lateral feeder is uniformly distributed. So L effective is L by 2. So that is the difference from the last and this one. For the primary feeder, L effective is total length. For while this L effective for lateral is L by 2, because this is uniformly distributed. So L effective is 3 by 2 mile. Now for this we have considered percentage voltage drop 2. So K into LE into SN. So LE is given for lateral is 0.002%. So 0.002% voltage drop per kVA mile, and LE is 3 divided by 2 into mile, and this SN is 500 kVA. This is given here 500 kVA. So this will come out at 1.5%. Now they are asking about total percentage voltage drop. So we have to include this main feeder and lateral both. So total percentage voltage drop is voltage drop 1 plus voltage drop 2. So first case we got 3% and this second case we got 1.5%. So total will be 4.5%. That is the answer B. Very nice. So let us move to the, in the problem any doubt?
Clear, sir.
So let us move forward to the last problem. So in this, they have told you to consider an octagon shaped distribution substation service area, and the substation served by 8 primary feeders. The substation is located at the center of service area. The length of feeder is 8 mile long. Determine the service under the feeder is a square mile. Service area in a square mile. So I discussed for octagonal shaped distribution service area in the slide also. Means how you can find for octagonal. Sir has discussed for a square and hexagonal shape. Ganguly sir has discussed for a square and hexagonal substation service area. Similarly, you can find for octagonal shaped service area, substation service area also. So here they have given the octagonal shaped distribution substation service area. So octagonal shaped means number of primary feeders is 8. Octagonal shaped substation service area. So that means number of primary feeders is 8. Number of primary feeders is 8. So they are asking about area. So what is the AN expression? Anyone remember? If anyone remember this expression, AN expression, you can tell. Area served by one of the N feeder. So AN is AN expression. Anyone knows? AN expression is ln square into tan theta. Right? This expression is important. So and tan theta is ln square, and tan theta is 360 degree upon 2n. So they are asking about for n equal to 8. So substitute n equal to 8. So a 8 L 8 square and 360 upon 16. So that will come out as L 8 square and 22 degree, 22.5 degree. So the length of each feeder is given as 8 mile. So it is 64 mile square and 1022.5 degrees 0.4142. We will get 26.5019 mile square. Correct answer is A, 26.509. So I have done with this previous assignment. Now I will just quickly go through other year assignment. So you can, I will just upload this assignment also, the past 2 year assignment also. So you can have idea about what type of question being asked in the previous assignments, and with the help of that you can solve your current assignment, and that will be helpful for your exam also. So in yeah, so this assignment little bit you have to understand, and I will suggest that if you know the expression and terminology clearly, then it is very easy, and if you don't know the under expression carefully, then it is very tough. Like here, first thing is that ln. Ln is length of each feeder, length of primary feeder means like, and then come as an means area served by one of the feeders, a4, a6, a8, and then come as sn. Sn means kVA load served by one of the feeders, and that is s4, s6. And what is sn term? Sn term you write d into an. D is load density and a is area served by one of the n feeders. And then other term come as area, you know that this one expression ln square tan theta, and then this percentage voltage drop. Percentage voltage drop we write it as k into le into sn. That's all. So these things you have to keep in mind. So let us quickly.
Sir,
So
what is the load density? What is the meaning?
load density. So we write percentage voltage drop k into L into Sn. So and in Sn term we use load density term d into An. So here d is load density, and this is given as kVA per kilometer square. So from this like for rectangular service substation, suppose this is primary feeder and this is substation, and it is having rectangular service area, and these are laterals, and it is having different loads, and they are uniformly distributed. Uniformly distributed means then it is having some load density, means what is the kVA per kilometer square, like it is 10 kilometer long, 10 kilometer long. This L is 10 kilometer long, so L is given as 10 kilometer long. So L is given as 10 kilometer. So now suppose this primary feeder is serving a load of how much? Serving a load of, let us say, 90 kVA. Serving a load of 90 kVA. So per kilometer, how much load it is being served? So that is load density per kilometer square per area. Means like this is 1 unit of area, then this is another unit of area, this is another unit of area. So per unit of area, how much load is being served? So that is load density. The load being served per unit of area, that is load density. So it is very simple. It is serving 90 kVA. So its load density will how much? 90 kVA, and its area is 100 kilometer square. So its load density will be 0.9 kVA per kilometer square. So in this area, the load is 0.9 kVA. And another set, it will be similar, gets added up. So just correlate with unit of area. Not in this set, you have to go per unit of area. So it is much big division. So just see that. I hope it is clear to you.
Yes, sir. Thank you.
So another, so already we have, don't have much time. So let us just go through another assignment for 2023. We have solved this type problem that is based on K constant, and then effective length, and again voltage drop. This is substation size, and similar type problem asked in your current assignment. Length of each feeder, voltage drop, then voltage drop again. If number of feeders get double, then voltage drop will reduce by half, and load density double means voltage drop will be also doubled. And for parallel operation, which may not mandatory. Then again transformer operated in parallel. Now for 2022 is one question is based on total power loss. We also have to remember this total power loss term. Means if you are having rectangular shaped substation service area, then total power loss is 1/3 of IS square RL. Here effective length is 1/3 of L. And so this is for rectangular substation service area. Anyone remember what is for rectangular substation service area? This effective length
2/10.
2/10.
2/3.
No, that is 8L/15.
Yes, 8/3.
8L/15. So effective length is very important. If you know the effective length, then you can easily write the expression of voltage drop and total power loss. Again, this is for voltage drop for rectangular service area, and we have solved for thermally limited feeder, how we can find the length of feeder. Then again, percentage voltage drop, feeder capacity is feeder capacity S4, that is S4 equal to D into F4. Substation size is TS4. TS4 you can write N into Sn. Percentage voltage drop. Percentage voltage drop. So that's all. Any other thing you want have? Any other concern you have, any suggestion you can tell me. Otherwise we can close session.
Are you uploading this 2023 also, sir?
In the slides, in the means PDF, you can see all the
Okay.
solutions.
Hmm.
Are you able to get the PDF of
Yes,
this
yes.
PPT?
Yeah,
Yeah,
we are referring that one.
yeah. Okay. Any other thing you want to ask?
Nothing, sir. Thank you.
Since we have
Okay.
12 weeks of courses, so from each week we'll have roughly 5 questions to the final. Is it final exam?
In the final exam, I am not sure, but
How many questions will be there?
it's like similar to GATE exam. Maybe in GATE, variation is less because only one course is there, but moreover similar to GATE exam, and it is more depending upon the course instructor. Ganguly sir is more, he can have the authority to decide what type of question, but
English sir
like
said around 50 to 60 questions. If it is 60 questions, 12 into 5. From each week we'll have 5 questions.
yeah, correct. That's why I told you now. In GATE exam we have 65 question. So just like that, 60 question, and some questions, all questions will have 1 mark. I'm also not confirmed.
No, Mark, he didn't say anything. He said 50 to 60 questions.
Then if it is having 100 marks, then some questions may be of higher weightage and some question may be less weightage.
Yeah.
Time is around 3 hours or?
Yeah, 3 hours. Time is fixed. Time. I can surely say that it is 3 hours.
3 hours. Okay.
If you having well understood, and if you are fluent in solving problem, then you may go in 1 hour also.
Yes, yes.
You can complete in 1 hour.
You are research holder, sir?
Yeah, I am also 4th year PhD student.
Okay.
4th year.
Can you share your number, sir? If you don't mind.
Yeah,
In
why not?
chat box.
Yeah, I can write. You can. We are from the same domain, so I am not hesitating in getting the contact number. So you can mail me also. No problem. I am working on this control of converters in a smart transformer based distribution system.
Oh, okay.
Okay. Okay. So thank you for attending session, and we will meet on the next Sunday.
Sir, what you say? A smart transformer, matlab what's?
Smart transformer is basically solid state transformer that is having another advantage like communication features and intelligent control features. Do you know solid state transformer?
Yes.
Solid state transformer means like it came earlier, but a smart transformer basically this term given by Professor Marco Ligre. So last year I went there. Last year in Germany I had worked with Professor Marco for 3 months. So we have one recently paper accepted that we worked there in TI,
Uh,
Transistor Industrial Electronics.
that is also energy rating,
A
star rating.
smart transformer generally be for higher voltage, higher power level. Like if you use for lower power rating, then it is not commercially good, because distribution transformer that we have, binding transformer, low frequency transformer, then that is cheaper than a smart transformer. So based on your advanced control, you can manage, based on your advanced integration of smart uh, control, you can have, you can just manage this cost and functionality, because cost is higher.
Can you
Okay.
repeat the transformer, sir? Can you repeat the transformer name?
Smart transformer, it is this term came from solid state transformer only.
Smart transformer.
Yeah, this power to is transformer only.
It
Smart
is used
transformer,
in transmission line only.
yeah, it's like in HVDC, you can also use.
Generation.
Yeah, no, generation not. It is used for transmitting the power, either
Okay.
for MV voltage level or for low voltage level. So you
And
can refer this Professor Marco Legere paper and our guides Professor Chandan Kumar. They have so many papers on smart transformer.
It is available in commercial or still in research field?
No, there are so many papers. So they have one good project in Germany that
No, I am asking about this smart transformer is available in commercial. It is using in utilities nowadays.
in European country they are using,
Oh, okay.
like for renewable energy integration, not for. I don't think they are using for supplying power to the customers like households. But for renewables, for integrating renewables, they are using it.
Okay.
sir, where we get the assignments, yeah, either research paper of the smart transformer.
IEEE Explore, your college has this IEEE license.
No,
IEEE is purchased.
no, sir, we have not IEEE license.
So you become the member of IEEE, then you have access of IEEE Explore.
Then,
Membership is very cheaper, very cheap. It's
okay.
like 1,500 or 2,000 rupees per year. And if you are having member for a long year of time, then it is very useful for your academic career. If you are in want to be anywhere, means generally it is useful for every, means like those who are in industry also. But for academic, it is very compulsory, because this seniority will increase based on the how long your membership there for IEEE
Okay, personally, we can take the membership.
membership. Yeah,
Okay.
if you are having membership, then you can access the papers. And like there is a student member, then senior member, and the big term is that fellow that you will achieve. That means like in your old age, when after getting so many experience, after publishing so many papers, you have long contacts. It's very reputed one. Those who become IEEE fellow.
You have personally taken your institute. Obviously, your institute have been
Yeah.
subscription or taken, but you are taken personally.
Yes, we have to take. Otherwise, how we will publish paper? It's compulsory for industrial electronics. It is compulsory. You should remember. And how without a membership, if you submit paper also, it will charge will be very high. So it's better to become member and then you submit your paper. Then you will be in the advantageous position. Membership is cheaper than submitting your paper. This charge.
Okay, okay, okay.
Okay,
What's the membership charges, sir? 15 to 20K.
it's in dollar. It depends. Like I think $15, $20 sometimes.
Okay.
I've taken for society membership. It almost like a power energy society, and then in industrial electronics, and then application society, and then power energy society. So for a society I had taken, and one is IEEE membership. So five it cost almost 4,500 each year. I'm paying 4,500 4,000 in the INR.
Okay, sir. Okay, sir. Thank you. Thank you for your information.
Okay, so good night, and we will meet in the next session.
Good
Okay,
night,
good
sir.
night, sir.
Good night.